Today we're going to talk about the explicit geometric sequence. So our first example, a bouncy ball is dropped such that the height of its first bounce is 48 feet, and each successive bounce is 50% of the previous bounce's height. So one key word here is that it says first. So with sequences, it will either say first or one. So if it said bounce one, that's going to indicate that this is a sequence instead of an exponential equation. So our first bounce is 48. Our second bounce is 50% of that. So that would be 24. Our third bounce is 12. Our fourth bounce is 6. Our fifth bounce is 3. So we're going to plot these and see what type of shape this graph is going to make. And as we can see, this isn't following in a straight line, like a linear equation. This is following more of an exponential equation where it's curved. The issue is we're not going to connect it. So just like with arithmetic sequences, with geometric sequences, we don't want to connect the dots because that would mean if we connect it, that means that all these numbers in between are included. And we can't have 1.5 bounces or 2.5 bounces. So what we want to do is leave it unconnected because that means we only use the whole positive numbers, our first bounce, our second bounce, our third bounce, and so on. Another weird thing with sequences is that we're not starting at 0. We don't have a 0th bounce, right? We start at 1 because that's our first bounce. Typically with exponential and linear equations, you would start at 0 at the y-intercept. That's our starting amount. But with sequences, your starting amount is at 1 instead of at 0. All right, so geometric sequences look like exponential equations. They're going to have that curved shape. When we look at our equations, we're going to have exponents in the equation. And they follow the pattern of exponentials. So here we can see this pattern is dividing by 2, or we can call it multiplying by 1/2. So just like with exponentials, geometric sequences will multiply or divide. However, there are some things that make them different from exponential equations. So with geometric sequences, we have to use whole positive numbers, which means we are not going to connect our dots. Because if we connect them, that includes all the decimals in between. So only whole positive numbers. We're going to start at 1 instead of at 0, where we typically start with our exponential formulas. And we're going to look for words like first or 1 to indicate that we're using a sequence instead of start or begin. Those would be the words for exponential equations. All right, so with exponential equations, we would have something like y equals a times b to the x. So this first number, our coefficient, this is where we start. And then this number is our base. That's what we're multiplying by. We also call that our multiplier. Right, and then we have our exponent. So geometric sequences are really similar to that. We're going to have a sub n, which is the same as y. That's our term value. So when we look up at our table up here, our y's were the actual height of our bounces. So that would be our term value, is the actual height of the bounces. And then a sub 1 times r, and then n minus 1 up in the exponent. So a sub 1 is our first term. That's our coefficient. Very similar to over here, it's where we're starting. It's just that with exponential equations and geometric sequences, you start somewhere different. With this one, it's your y-intercept, which is at 0. Here, it's your first term, which is at 1. So it's a little bit different. And then we have r. This is our common ratio. So this is what we're multiplying by. It's the same as our multiplier or our base. And then up in the exponent, we have n minus 1. That's the same as x. That's our term placement. Just like our table at the top, x was which number bounce we were on. So our first bounce, second bounce, third bounce. So this is very similar to our exponential equation. It's just that we're starting somewhere different. And so our exponent has to be different to account for that. Since we're starting at 1 instead of at 0, we have to put n minus 1 up in the exponent so that our equation actually works. So explicit formulas help us to find any term in the sequence. So if we want to find the 100th term, we can just plug in a 100 for n and figure out how high our bounce would be after 100 bounces. Right, so to find our explicit formula, we only need two things. We need our first term and our common ratio. So on our top example, our first term was 48. That was our first bounce, was 48. And then we were multiplying by 1/2. So remember, this is our multiplier. So we are dividing by 2, but it's always in terms of what we're multiplying by. So our first term is 48 times our common ratio to the n minus 1. And that is our explicit formula. There's nothing we can do to simplify that. So to find any term number, we want to figure out what term number we're looking for and plug it in for n. For example, if it said find a sub 5, that means find the 5th term. So we would take our equation and we would plug in a 5 for n. And you just want to make sure that you either put this in parentheses or go ahead and simplify. 5 minus 1 is just 4. Just to make sure all of that exponent is actually in the exponent in your calculator. And when we put this in our calculator, we get 3. So our 5th bounce has a height of 3 feet.